Hi, welcome back to the lecture series on abstract magic theory. Hope you all will be fine. We continue this lecture on the product measure that we had discussed in the previous two lectures. So let's start this lecture with the following theorem. If we have two sigma finite measure spaces x and y, so let x and y be two sigma finite measure spaces. Let x as mu and y, this is summation, and nu be two sigma finite measure spaces, be two sigma finite major spaces. Then this x cross y, s tensor sigma and mu cross nu is also a sigma finite major space, is also a sigma finite major space, and mu cross nu star is equal to mu star cross nu star on this space, on this summing, which is lambda mu tensor lambda nu. So this theorem is very simple. It's not too difficult, because the extension of outer measure on a sigma finite measure space is always unique. Using that property, uniqueness of the outer measure generated by a measure, you can see this mu cross nu whole star is equal to mu star cross nu star on this. Okay, so the extension of the measure, okay, the outer measure generated by mu is unique for a sigma finite measure space. So this is already done in the first course of measure theory. So you can see this from that lecture series. Okay, yeah. If you want to see its proof, you can see the page number for the proof. See page number 207. Okay, you can see this page number. Now we start our next section, that is the x section and the y section of the sets. Suppose we have two arbitrary sets, and how can we define the x section and y section of some particular subset of that product set? Okay, so let's discuss some definitions here first, then we state then we prove our main theorem. Okay, so suppose we have two sets. Let x and y be two non-empty sets, and A is the subset of x cross y. Let A be a subset of the set x cross y. Okay. Here these x and y, they are any sets, any non, they are not major space in general. तो यहाँ पर जो x और y है ये कोई भी सेट्स है, so they are not major spaces in general. in particular. In general, they are general sets. Okay, they are general sets. We don't have any structure on those two sets, x cross on x and y. A is any subset of x cross y. Now let's define the sections now. Okay, and this x belongs to x. So for to define the section, or you can say x section, we choose a point x in x, then x section, then what's x section, then x section of A, then x section of A is a subset of y, is a subset of y, is a subset of y defined by ax is equal to, it's a subset of y, those points of y such that the ordered pair x comma y belongs to A. Okay, this x is fixed. Similarly, we define y section. Similarly, if y belongs to y, then the y section, of A, then the y section of A, then the y section of A is a subset of x, is a x section subset of y, and y section subset of x, is a subset of x which is defined by this A power y. So that's a notation for y section. Those x belongs to x such that now here y is fixed, x comma y belongs to A. Now let us see the geometric meaning of x section and y section. So let's suppose our x space along this direction. Okay, x-axis, treat this as x space and treat this as y space. So it means that this whole plane is actually x cross y. Now let's take any subset of, see, this is a set A, suppose. Okay, this whole is set A. Okay, this is set A. Now if you want to see, suppose you choose a point x here, you want to find the x section which is a subset of y, it is those points such that x comma y belongs to A. So what's this x section? This x section will be, let's take this line here, this. Okay, so let me sorry, let me erase it first. Okay, this is the subset A of x cross y. That's the shaded region A. Now let's find this set. Say this is the point A here. This is the point x. Then this portion, which is subset of y. So don't need to write here this one, only this one. This red line, which is a subset of y. It's your ax. Okay. Can treat this. Okay. this is it. This is y-axis. Now this one, this one, okay, this one, this is ax. Actually ax is this, it's a subset of y. This is y here, this is the set y here, and that's our ax, okay, which is subset of y. Now if you want to find a y for any particular y, you choose a point y here, you choose a point y here. Let's choose this point y here. Then you have to draw the horizontal line here, and you have to check this the intersection of horizontal line this with this set, with the subset A of x cross y. Which is ay. This is the point y here, okay. Then you had to choose this from this point, okay. So this one, and now draw the perpendiculars on this x-axis, and see this one. So that's your ay, which is a subset of this is ay. So this ax, which is equal to that one, it's a subset of y, and ay is subset of x. This is x section, and that one it's your y section. Okay, now let's prove the following theorem. It's the main theorem of this section. To prove that main theorem, let's state the following statements here. Let's first verify these statements. Let's verify the following statements. We have the following identities for these show that following identities hold. Show that the following identities hold. So what are the identities? First identity is the section of unions, okay. If we have a union I is in the index set I, say, if you want to find its section, it's equal to union of sections. Section of the union is equal to union of sections. Union of sections. And the second part is regarding the intersections. Section of intersections is equal to the intersection of sections of x sections, okay. Sorry, it's for x section, okay. Now similarly we have for y section union and intersection, replacing these x sections by y sections. So we have two more statements, and finally we have the difference, which is equal to ax minus bx, and same is true for y section, which is equal to ay minus by. So we have actually total, we have how many statements we have? Two statements for union, two statements for this x section, which is for union and the intersection, and two statements for the y section for union as well as intersection. That's four. There are four statements, and this is the for x and this is for y. Total we have six statements actually. So you verify these six statements. It's very simple. Now we state our main theorem of this section, which is the following. Let E be mu cross nu measurable set. Let now onwards these x and y, they are measured spaces. Okay. Let E be a mu cross nu measurable, be a mu cross nu measurable set, subset of x cross y, subset of x cross y, satisfying that its measure is finite, satisfying mu cross nu star of E is finite, its measure is finite. Then for mu almost all x's, then for not for all x's, almost all x's, mu almost all x's means this property does not hold outside. This property only holds outside a set of measure 0. It's almost everywhere actually. For mu almost all x, mu almost all x, the set Ex is a new, because it's a subset of y, it's a new measurable. It's a new measurable, but it's a function of x actually, but it's new measurable because it will vary with x. Is new measurable subset of y, subset of y, and the function which maps x onto, because now it's measurable, we can find its outer measure, nu star of Ex. So this is a function of x. Okay, so for this x maps onto nu star of Ex. It's a real valued function because nu star of Ex is a real number. This defines an integrable function. So this is a function from x to r actually. Okay, because x is a point of x, and this nu star of Ex is a real number, x is not a real number. But here it is a finite because the measure of E is actually finite. So you have to show that this defines an integral function. This defines an integral function on x. What will be its integral? That's very interesting. Such that the integral of this, the integral of this function nu star of Ex d mu, it's a function of x here, so we have to do this integration with respect to x over the space x. Okay, over the space x, it's equal to mu cross nu star of E. Its integral is finite. Okay, it's integrable function actually, and the value of the integral is mu cross nu star of E. It's a finite number. So this is very interesting. The integral of this function is equal to the outer measure of the set E. And similarly, we can define for nu almost all y's, we can define the set E power y, the y section of this E, which is a mu measurable subset of x, and the function which maps y onto mu star of ey defined as an integral function. That so that is similarly. So we have actually two parts of this theorem. We will prove only one part. The second part follows a similar lines. Similarly, for nu almost all y, the set e power y with subset of x is a mu measurable subset of x, is a, that you have to verify, it's a mu measurable subset of x, and the function which maps y onto mu star, because this ey, it's a subset of x, mu star of ey, it's again a real valued function on y, defined as an integral function, defines an integrable function such that on y, such that its integral on y d nu, it's equal to, it's same, mu cross nu star of e. So that means these two integrals are actually equal. Integral over x nu star ex is same as integral over y mu star ey. Both are equal to mu cross nu star of e. So let's prove this theorem. We prove this theorem in 4 steps. And by symmetry, we prove only the first part and not the second part. We prove this theorem in 4 steps. We prove this theorem in 4 steps. So step 1. What's step 1? In this step, we assume that this E is a member of S cross sigma. It's a member of semi-ring. Assume that this set E is a subset of X cross Y. It's of this type, A cross B, and we assume that it is the member of, it's a measurable subset, but we assume that it's a member because every member of this semi-ring is a measurable. It's measurable. Suppose it belongs to this collection. Okay, maybe outside of this. So let's take, in this step we assume that E is a member of S tensor sigma. Now what's Ex? So first we verify that our Ex, which we need to show that it's a measurable. Ex is equal to B if X is in A, and this is the empty set if X is not in A. If X is not in A. Okay. So this Ex is B if X is in A. That we have to verify first. So how do we do this? Our Ex, what's the definition of Ex? We have, or we show that this suppose X in A, we need to show that Ex is equal to B, but what's E? E is A cross B X, the X section of A cross B. It's obviously B in that case. That you can easily check, or you can see it's You can verify it geometrically as well, or you can see it. You can verify it using set theory inclusion property. Okay, we verify this ex is subset of b and b is subset of ex in case x is in a. So we have this. If let assume that let's write. Okay. So if let x belongs to a. X belongs to a. So assume this y, it belongs to ex. So what does it mean? That it means that x comma y belongs to e by definition of ex. So this implies x comma y belongs to e, which is equal to a cross b. That implies y belongs to b, so which implies that ex is subset of b. Now assume that this y is in b, but where is x? X is already in a, which implies that x comma y is in a cross b, which is your e, which by definition implies that y belongs to ex. That's the definition of ex. Those y's say that x comma y belongs to e. So this implies our b is subset of ex. So therefore ex is equal to b. That's simple. Now second case, if x is not in a, we show that b is empty. We show that b is empty set. For if y belongs to b, but x is not in a and y is in b. For if this y, there is a point y which is in b. Sorry, we have to show that ex is empty. We have to show that this ex is empty, not the set b. We show that this ex is empty. For if y is in ex, okay, y is in ex. So this implies by definition x comma y belongs to, the definition of ex belongs to e, which is equal to a cross b, which implies x is in a contradiction, because x is not in a contradiction. So thus we have proved that ex is equal to b if x is in a and ax is equal to the empty set if x is not in a. So in both the cases ex is measurable, because since our b it's a member of, because a cross b belongs to S tensor sigma, it's a member of sigma, and the members of sigma are nu measurable. So therefore in both the cases, if x is b, which is nu measurable, and the empty sets are always nu measurable, so therefore e x is nu measurable, is nu measurable for all x, not almost everywhere. This is true for all x and x. So that verifies this ex is nu measurable. Ex is nu measurable. Now next we'll see that now this you can easily verify that this nu its measure is, because it's either b or empty, it's a member of sigma. Actually we don't need to write here nu star, because nu star is extension of nu actually. So nu star is same as nu on sigma, or you can write it as nu star. Okay, there's no harm, which is equal to nu ex, and that you see it's equal to measure of p, nu of b, into characteristic function of x. So that's again simple. Suppose if x is in A, then ex is equal to b. It has already verified, therefore this will be nu of b, and if x is in A, this is nu lambda of ax, this chi of ax equal to 1, this side is also equal to nu of b. Okay, both nu of b equal to nu of b. Now if x is not in A, then chi a of x equal to 0, so therefore this side is equal to 0, this part is equal to 0. So if x is in A, then chi a of x equal to 1. Okay, so therefore this side is equal to nu of b, and this side is also equal to nu of b, because ex is also equal to b if x is in A. Now second case, if x is not in A, then this will be equal to 0, nu chi of ax will be equal to 0, so this side will be equal to 0, and this side is also equal to 0, because this will be equal to nu of phi, because if x is not in A, whenever x is not in A, ex is the empty set, so that means this will be nu of empty set, that's equal to 0. Both sides are equal to 0. If x is in A, both sides are equal to nu of b, and if x is not in A, then both sides are equal to 0, therefore they are equal. They are equal. Okay, so both the sides are equal. This is that's very simple. Let's name this star. This is true for all x belongs to x. This is true for all x belongs to x. Now since this measure is finite, and since mu cross nu of A cross B, because it's a member of summing, we don't need to write here this star here, that's equal to mu of A into nu of B, which is a finite. It is given that this measure is finite, so we have following two possibilities. So we have following two possibilities. Since it is finite, so first possibility is that both may be finite, both are finite. The first possibility is both have finite measure, and second possibility, if one of them has infinite measure, second must be 0, because if second is non-zero, the non-zero into the infinity will be equal to infinity, which is not the case because it is always finite. So in the second case, if one of them is infinite, say mu of A is infinity or mu of B is infinity, then second must be equal to 0. So these are the two possibilities actually. So let's discuss these two possibilities. The first possibility, both अगर दोनों का मेजर फाइनाइट होगा, if both A and B have finite measure, so this star gives x to, which maps x to nu star of ex, is an integral function. So actually it's a step function in that case. It's a step function. Okay. So in this case, our star shows that the function which maps x onto nu star of x, in that case nu star of ex means nu of ex. Okay, star showed that this function is an integrable function, Why it's an integral function? You can see from the star. Okay, star is this. So this is actually step function because it is only two values. One is nu of b and second is 0, because whenever x is in A, it's equal to nu of b, and whenever x is not in A, it's equal to 0. So it's a step function with values nu of b and 0, and both the values are finite, so it's actually a step function, and we know that every step function is integrable. So that's why it's integrable. In fact In fact, it is a step function. It is a step function. So it has only two values, nu of b and 0, and nu of b is finite because we have assumed that both a and b have finite measure. So it's a step function, and every step function is integrable. Now let's find its integral, because we have to show that the integral of this function equal to the measure of e. So and the integral over x of nu star of ex, a d mu. This is equal to integral of nu of b, because nu star of ex equal to nu of b into characteristic function of a d mu. So that's equal to nu of b, that's equal to nu of b. ये इंटीग्रल से बाहर आएगा because it is independent of x, into chi a of x. The integral of this function is equal to mu of a. It's a step function. Its value is this, which is equal to mu of a into nu of b. That's equal to mu cross nu of a cross b. That implies the integral over x of nu star of ex d mu is equal to mu cross nu of e, which is same as mu cross nu star of e, because e is a member of summary, and this mu cross nu star is the extension of mu cross nu. So in that case, we have done integral of nu star of ex is equal to the outer measure of e. Now possibility second, either a or b has infinite measure, तो इस केस में क्या होगा? We assume that a has infinite measure. Okay, so assume that the measure of a is infinity, then the measure of b must be equal to 0, because as mu of a into nu of b is finite. So measure of a is infinity and measure of b is 0. So other set must be equal to 0. We see that from star. Okay? From star, this nu of ex equal to 0 almost everywhere with respect to the measure mu. Okay, why it's equal to 0 from star? You can see from star. Let's see the star equation. This is the star. Where is star? Here we have star. So in that case, we have assumed that let me see first the case. We assumed that this mu of a is infinity and nu of b is 0. So measure of b is 0. That's the case. Measure of b is 0. Measure of b is 0. Okay, this is star. Measure of b is measure of this set is 0. We have to show that this is equal to 0 almost everywhere. So this is 0, and this one has either 0, it is either 0 or 1. So if this is 0, so it's always equal to 0, because this part is always, whether x is in a or x is not in a, it's always equal to 0. So in that case, nu star of ex always equal to 0. So it's not almost everywhere, it's always equal to 0, not almost everywhere. Then this is equal to 0, this is equal to 0, not almost everywhere, for all x. Okay, it's for all x, for all x in A. And now second case, if mu of A is 0, if mu of B is infinity. Okay, उस केस में आपको देखना है. Mu of B is equal to 0, then mu of A equal to infinity. In that case, you will see that mu of Ex is not equal to 0 for all x, but almost everywhere. Now mu of B is equal to 0. Okay, mu of B is equal to infinity. Sorry, mu of B is equal to infinity. Mu of B is equal to infinity. Then this is equal to 0. Mu of B is equal to infinity. Then this one equal to 0. Okay, let's see the star again. Mu of A equal to 0. Okay, here. So mu of A equal to 0 here. Mu of A equal to 0. A is equal to 0. So you will see, if x is in A, it's equal to mu of B, which is equal to infinity. Okay. But if x is not in A, it's equal to 0. And if x is not in A, so outside of A, it's equal to 0. But the measure of A is equal to 0. So outside of A, it's equal to 0. Outside of A equal to, if x is not in A, then it's equal to 0. So let's see it like this. So let me write it like this. Okay. If this and we have for x in A, what will be this nu of Ex, which is equal to nu of B, that's equal to infinity. And x not in A, nu of Ex equal to 0. But mu of A is equal to 0. So outside of A it's equal to 0, which implies that nu of Ex equal to 0 almost everywhere. So in the first at the first step, since we have two possibilities here for this case. For the second one, either A or B has infinite measure, then we can choose two possibilities again here. This is infinite, this is 0, this is 0, this is infinite. In both the cases, in the first case we have seen that this is always equal to 0. Nu of Ex equal to 0 for all x in X, not in A, for all x in X. And in the second case, we have seen that this is equal to 0 almost everywhere. Therefore, in general, we can say that this function nu of Ex equal to 0 almost everywhere. It's equal to 0 almost everywhere. So thus nu of Ex equal to 0 almost everywhere in both these sub cases. Okay, this is equal to 0. So therefore its integral must be equal to, because it's a 0 function, so therefore the function which maps x onto nu star of Ex is an integrable function, and what will be its integral? And its integral equal to 0 because it is 0 almost everywhere. And integral over x nu star of Ex equal to 0, which is same as mu of A into mu of B, because one of them is equal to 0. So it's equal to 0, which is equal to mu cross nu of A cross B, and which is equal to mu cross nu star of A cross B. So that proves the step first completely. So in the step first, we have seen that if the set E is a member of semi-ring S tensor sigma, then result holds. Now we have step second. Second. Okay. In the step second, we will assume that E is a sigma set of S tensor sigma. So assume that E is a sigma set of this semi-ring. Okay, then this is actually the disjoint union of members of S tensor sigma. So let En be a disjoint members of S tensor sigma, such that this E is A cross B, such that this E, which is equal to A cross B, is union of En's and runs from 1 to infinity. So then we have already seen that this what will be the x section of this. So what's Ex? Ex will be x section of this. That's union of the x sections that we already verified. Enx, and we know that Enx is measurable because En is a member of S tensor sigma. So whenever in the step first, when we have seen that if E is a member of S tensor sigma, then Ex is measurable, and here En is a member of S tensor sigma, therefore Enx is measurable, and the union of measurable sets is measurable. Which is measurable as Enx is which is a new measurable. Okay, new measurable, as Enx is new measurable by step 1. Okay, as Enx is new measurable, Enx, so union of measurable sets is measurable here. So Ex is made. That proves the first property. Now in the second property, we have to show that it's nu star of Ex is defined as an integrable function. It's new measurable for all x. Okay, it's for all x in x, as this is new measurable for all x in x by step first. Now I'll define the following sets. Define the following functions. Define f of x equal to the nu star of Ex, which we have to show that it's integral function, and let's define this one, fn x, which is summation I runs from 1 to n nu of, don't need to write nu star here because they are members of S, tensor sigma. Okay, this one. Okay, for all x in x. Now we know that this nu of Eix is integrable by step first, since nu of Eix is integrable. This is integrable. Is integrable by step 1. So therefore fn x is, because sum of the integral function finite sum, therefore fn x is integrable. Therefore fn x is integrable for all n greater or equal to 1. For all n greater or equal to 1, it's integrable. And not only this, and the integral over x of fn x d mu, it's a finite sum, its summation I runs from 1 to n integral of nu of eix, okay, into d mu, and that's equal to summation I runs from 1 to n. What's this integral? It's actually the measure of the set. It's measure of set. It's mu cross nu of ei. And that you can see this, if n is approaching to infinity, it will increase to, this will increase to mu cross nu star of e, which is finite. So integral of fn x is finite. It's a monotonic increasing sequence actually, because fn is a summation. It's a sum of the positive numbers. So if you increase the value of n, you will get this fn x will increase. Okay, fn x is less or equal to f2x, because f2x is sum of two non-negative numbers actually. So f1 is less or equal to f2, f2 is less or equal to f, and so on and so forth. It's an increasing sequence, and integral fn, limit of this integral is finite, because limit of this integral mu cross nu star of e. As n is approaching to infinity, it's a disjoint sequence. You can easily verify it. It's not too hard to verify. This is because it is a mu cross nu star of union ei runs from 1 to n, that will approach to mu cross nu star of union en runs from 1 to infinity. That's already discussed in the first course of measure theory, these properties. Okay, monotone property of measure actually, because the union ei n runs from 1 to infinity is equal to e. So that you can treat as the increasing sequence. You can treat this e1 as the first set, e1 union e2 as the second set, e1 union e2 union e3 as the third set, and this will be the increasing sequence of sets, and then you can easily verify this one. This limit is actually equal to the e, because the union is ultimately equal to e. So that's very simple. Mu cross it will approach to mu cross nu star of e, which is equal to finite. So here you can apply the Levy theorem. What's Levy theorem? What's the statement of Levy's theorem? Which is the statement of Levy's theorem is that given a sequence, increasing sequence of integral functions such that the limit of the integral of fn is finite, then the limit then we can define a function f which is the limit of fn x, such that that function f defined as an integral function, and the limit of the integral of fn is equal to integral of the limit of fn. That's the Levy's theorem, and this fn, it satisfies the properties of Levy's theorem. So therefore fn satisfies, therefore fn, sequence fn satisfies the properties of Levy's theorem. Satisfies the properties of Levy's theorem. Satisfies the properties of Levy's theorem. Okay. And again, since now what's the limit of this will be into, what's limit actually? That's very important. Since this sequence en x is a disjoint sequence, is they are subsets of, is a disjoint, because e is disjoint, en is disjoint, so en x is disjoint sequence, and they are not subsets of y, and they are also measurable, so they are members of sigma actually, in fact, because en is a member of S tensor sigma, so they are members of sigma. So we have now, using these properties, Levy's theorem, fn satisfies the condition of Levy's theorem, and this is the disjoint sequence, and we will see that nu star of ex it's equal to summation and runs from 1 to infinity nu of enx. Okay, nu of enx. So if this is the case, nu star of ex actually this infinite series, so it means that our fnx is actually increases to fx, because fnx summation I runs from 1 to n nu of eix is actually fnx, and that limit of fnx is the infinite series, which is equal to nu star of ex, and that's equal to fx. So fnx increases to fx, so therefore this satisfies the properties of Levy's theorem, and since this holds, so this equal to that hold for all this is for all x in x, right? This is for all x in x. So therefore f is an integral function. Therefore fx defined as an integrable. This is by Levy's theorem, and that those reasons which I have mentioned here, this whole thing, the limit is fx actually, and by Levy's theorem fx is integrable function. And one more thing is that, and integral of fx equal to limit and approach to infinity integral of fnx. So which means what's fx? Fx is integral of nu star of ex, which is equal to limit and approach to infinity. This fn, integral of fn is equal to the summation I runs from 1 to n summation I runs from 1 to n nu of eix. Okay, and that's equal to, and that okay, let's apply direct that part here. That's that integral is equal, that we already verified, it's equal to mu cross nu of ei. Okay, and that's equal to summation n runs from 1 to infinity. Let's apply the limit. N runs from 1 to infinity mu cross nu of en, which is equal to mu cross nu star of e. So that proves this integral of nu star, it's over x, okay, this integral is over x. So that proves this integral over x of nu star of ex equal to mu cross nu star of e. That proves the second step. Now we had two more steps, step 3 and step 4, that we will do in the next